Good morning, happy Friday, 8th graders. I wanted to do a quick review and really an overview of the beginning of Unit 8 because you do have a quiz in Khan Academy on lessons 1 through 5 that you should be turning in by 4 o'clock this afternoon. So I wanted you to have this brief overview to watch first, go through the lesson 5 questions that are assigned, and then go ahead and take that Khan Academy quiz. So I'm going to go ahead and share my document camera. Okay, and I'm going to start from the exit ticket the other day. It sounded like some of us were feeling a little unsure still about area. So I'm going to do a quick overview of just finding the area and the side length of a square, and then we'll move on from there. So for example, this is one just right out of our book on page 10. To find the area of a square, that's the inside space, okay? And so in this particular problem, we can count the number of units inside. We can also identify what the side lengths are. So if I count the side lengths, 1, 2, 3, 4, 5, I have a side length of 5. It's a square, so I know every side length will be 5. And then as a reminder, to find the area of a square, we take the side length times the side length. And anytime we're taking the same number and multiplying it times itself, we can use an exponent. So I have s to the power of 2. In this particular problem, my side length is 5. So if I want to substitute that information in, I have 5 squared, which is 25. 5 times 5 is 25. Again, this is on a grid, a unit grid, so you could just count up the number of squares on the inside, which would also get you to 25. Okay, and then as an overview of units, so I know some of us weren't sure in that exit ticket how to deal with units. So as a good reminder, anytime you're finding the side length of a square, you just keep the units by themselves. So we knew it was 5 centimeters as our side length, we would say 5 centimeters. If we knew it was inches, it would be 5 inches. If we didn't know the units, we would just say 5 units. Okay, we'll move on to area. We are multiplying units, so this is 5 units times another 5 units. So that gives me 25 units squared, or square units. So we might write it as units to the power of 2. You might see it as units squared, or you might see it as square units. So sometimes we talk about square feet. Okay, that would be an area of something to the power of 2. And then as a reminder, because we have done a lot of volume from unit 5, volume, if you remember, did our units to the power of 3, or units cubed, or cubic units. Okay, or cube units. If you said that, I know what you mean. Okay, so that's just a quick overview of area versus side length. Now, from there, we need to think about what is this relationship? Okay, a lot of what we do in math is dealing with relationships between different pieces of information. So I'm going to kind of think of the different relationships we've dealt with so far. We've talked about inverse operations before. Okay, so if I'm thinking about inverse operations, I think about addition and subtraction. Okay, those are what we consider inverse operations. Okay, another example would be multiplication and division. Okay, we can think about working backwards, right, or undoing an operation. Okay, and so that idea is really helpful to us when we're dealing with square roots. Okay, we had a square where the inside was 25 units squared. That was our area. And our side length was 5. Okay, so if we know 5 squared equals 25, this is our side length squared, and that equals the area. But sometimes we're going to know the area and we want to work backwards to find the side length. Okay, and so if we want to work backwards, we know the area. So we know the area is 25. What operation or what can we do to undo the area? Okay, so squaring a number is one form. We're going in one direction from the side length to the area. But going backwards, we're going to talk about using a square root. Okay, so if the area is 25, that side length is going to be 5. And we represent this as the square root of 25 equals 5 because 5 squared equals 25. Okay, another example would be the square root of 36. The square root of 36 is 6 because 6 squared equals 36. Okay, so this part under what we call a radical symbol, this is representing the area of my square. Again, we call this a radical symbol. And then when we find the square root of that number, it's going to give us the side length of our square. So that's an overview of just what are square roots? Where does this information come from? How is it useful? How can I use it when I'm dealing with different squares? Moving from there, we have something called perfect squares, and that's what I have on this paper. A perfect square is anything where when you find the square root, it equals a whole number. It means the side length of your square is a whole number, okay? And so if you have a square that has a length of 1, 1 times 1 would give you an area of 1. If you have a side length of 2, 2 times 2 would give you an area of 4. So the square root of 4 equals 2. Okay, so working backwards and forwards, when you do that square root of 4, it equals 2. We would call that a perfect square. We would call this a perfect square. We would call this example a perfect square because my side length in all of these examples equals a whole number. However, as you've seen in your beginning part of Unit 8, that's not always the case, okay? So sometimes we end up with squares that have areas that are in between that perfect square. It's not necessarily 25 as my area. It's not necessarily 36 as my area. There are many examples of squares that have areas in between that, okay? And so when we're looking, I'm gonna draw a number line, okay? And I'm gonna think about on a number line, let's just start at 0 because in a square, my side lengths are gonna be positive numbers. I won't be able to have a negative side length for a square. So let's say I have 0, I have 1, 2, 3, okay? Now I know that 3 squared equals 9, 3 times 3 equals 9. So the square root of 9 is equal to a side length of 3. So I can actually make these the same on my number line. 3 is the same thing. It is the same value as the square root of 9. And then 2, if my side length is 2, 2 squared equals 4. So the square root of 4 equals 2. So on my number line, 2 is equivalent to the square root of 4. Those are actually in the same exact place on the number line because they're equal in value. If I had 1 squared, 1 times 1, my area is 1. So the square root of 1 equals 1. So those go in the same place on my number line. So now I've graphed 3 different numbers, the square root of 1, the square root of 4, and the square root of 9. But let's say I have a square whose area is 6. So if I want to know the side length, that's going to be the square root of my area 6. You will notice that we jump in our perfect squares. A side length of 2 is square root 4, but then the next side length, that's a whole number, would be 3, but that's the square root of 9. So what do we do with these numbers that fall somewhere in between? Well, that happens a lot on our number line, right? We can graph numbers that are in between. And so square root of 6, I need to decide, what do I think that would be closest to? I know for a fact it's going to be between 2 and 3 on my number line. And I have to decide, is it going to be closer to 2 or is it going to be closer to 3? Well, if I had square root of 4, in between I have to have the square root of 5, the square root of 6, the square root of 7, the square root of 8, and the square root of 9, which equals 3. And if I think about kind of that halfway point, 4, square root of 4, and then square root of 5, square root of 6, this is kind of the halfway point. Square root of 7, square root of 8, square root of 9. Okay, so that square root of 6 is going to fall a little closer to the square root of 4 than the square root of 9. So if I think about kind of that halfway point, again, this is an estimate. I'm doing the best that I can. But maybe right about in that area, I would graph the square root of 6. Okay, so I'm able to estimate approximately where these imperfect square roots would fall by using a number line, okay? By just reasoning with the information I know about those perfect squares, the ones that have a side length, that's a whole number. So you can estimate that. Again, I haven't picked up a calculator. I haven't done anything that requires me to have some special resources. I'm just using what I know about numbers and the number line in order to estimate where this number might fall, okay? So now I want to talk to you about that square problem that was on your exit ticket, that Google form, okay? So on this particular problem, you were given a square, and I wrote out an explanation, but I think that math is easier if you can see it, okay? So sometimes it's easier to see an example. So this is the very same question you had, and I need to figure out the area and the side length of ACEG. Oh boy, so that's this square on the inside. Okay, on your exit ticket, it was broken into 2 questions. The first question asked you to find the area. The second question asked you to find the side length. So I'm going to use what I know about the larger square, and I'm going to subtract some information to find the smaller square. So for my large square, and when I say my large square, I'm talking about BHFD. So BHFD, that's that large square. And I know that this part of it is 6, and this part of my side length is 8. So if I want to know the side length for this larger square, I'm just going to add 6 plus 8, and that gives me 14. Now for a square, I know the side lengths are all the same. So if this side's 14, again, I'm still adding 6 and 8. This side is also 14, 14, and 14. Okay, so my side length equals 14, which means my area is going to be 14 times 14, and that happens to be 196. Again, my units are going to be units, squared, or units to the power of 2. But I don't want to know the big square. I just need to find that, get that information in order to help me with the smaller square. So I'm not finished yet. And now I'm going to really think about these small triangles. If I have the area of the large triangle, I need to subtract these pieces in the corner in order to find my remaining piece, which is this square in the middle. So if I think of this triangle here, okay, so I'm going to lay it on its side. I'm going to put this part on the side. That's 8. And then this part is 6. Okay, so that's one triangle. And so I'm going to match that triangle, and I'm going to lie my triangle 2 right on top of it. So if I envision it has a side of 6 and a side of 8, then this is my triangle 2. Together, those triangles will form a rectangle. To find the area of my rectangle, I just do length times width. So the area of those 2 triangles is 48. Okay, so this space that's being taken up here is 48. If I look at triangles 3 and 4, side of 6, side of 8, side of 6, side of 8. So I can kind of move these 2 triangles together to form another 6 by 8 rectangle. So that means I have 48 units squared and another 48 units squared. Okay, so that means triangles 3 and 4 are also going to equal 48. And so when I add this together, space that's being occupied by all 4 triangles is a total of 96 units squared. Now, if I know that the large triangle is 196, and I know that this information, those 4 triangles, is 96, I'm going to subtract that. Take it away so that all that's left is the square that I really want to know about. So the area of my small square is 100 units squared. So if the interior is 100, to work backwards, I need to find the square root of 100. So what number times itself, S times S, has to equal 100? And I know that the number that when I multiply it times itself equals 100, that would be 10. So my side length is 10. And because it's the side length, my units are just 1, right? It's just a single unit. So I don't have to square it or cube it. So my side length is 10 units. The last thing I want to do, dealing with square units before we move on to rational or irrational numbers, is I want to talk about what if you were given 2 perfect squares on top of each other. Okay, so for example, what if I was given 81 over 100? Okay, if you ever see something like this, we can still simplify this expression. You have all the tools you need. You just may not have seen it this way. So this is the same thing as taking the square root of 81 and dividing it by the square root of 100. So this is a nice way for me to look at it, to really break apart all the pieces. So now the square root of 81, what number times itself equals 81? Oh, that's 9. So the numerator is 9, and my denominator, we just did the square root of 100, would be 10. So the square root of 81 over 100 is equivalent to 9/10. So you can just break apart those 2 pieces. The last thing I'm going to show you is rational versus irrational numbers. We are almost finished. And so rational versus irrational numbers. how do you decide? How do you determine, is this rational, is this irrational? And there's two pieces of criteria that I look for when I determine if a number is rational or irrational. I'm asking myself, does the number terminate? Does it end, right? Think of the Terminator, right? Does my number end? Is there an ending point? So rational numbers are terminating numbers. So they terminate, meaning there is an end. Or, okay, and this is important, or they repeat. Okay, so when I'm thinking of a number that ends, I'm thinking of something like -10. I'm thinking of something like 1/4, where if I convert it into a decimal, 0.25, there is a clear ending. Okay, so I don't have to do anything special. These are a lot of the numbers that you've been working with up until this point. I could do something like 1/3. Now, 1/3 is actually equivalent to 0.3 repeating. So it does not fit this criteria. There is not an end. It will repeat forever. But it repeats, right? And my rational numbers can do either one. Okay, so that's a nice example of a repeating decimal, but that is a rational number. Irrational numbers never repeat and do not end. And we call that non-terminating. So this would be a non-terminating decimal. So one that I think of, one that you've used many, many times, maybe you didn't know it was called irrational, but pi. Pi goes on and on forever, but it doesn't repeat. There's no repeating there. Okay. Another example might be these non-perfect squares. Okay, these square roots that fall in between the whole numbers on the number line. So square root of 6. I'm going to show you very quickly what that looks like on a calculator. If I were to put in, so I would put in 6, right? And then I'm going to hit the square root button over here. This number, now my phone doesn't fit a number that never ends. It's going to go on and on forever. There's nothing my phone can do about that. It has to cut it off at some point. But this should be enough for you to recognize this number is not going to end. Okay, if my calculator had a bigger screen, it would continue going on and on. I also don't see any pattern that repeats. Okay, so that's an irrational number. Versus 1, so I said 1/3, so 1 divided by 3. You notice that's repeating. Okay, that's why it ended up on this rational side. What about a number like 2/3? Okay, if you have a number like this where the pattern, you can see a distinct pattern, but the last number is off, that's caused by the fact that your phone or your calculator has to end, and so it's rounding that last 6 up. Okay, so if you have a repeating or a pattern that's happening here, you can just disregard that last number because that's something that your calculator is doing. That's not something that's true to the number. And so 2/3 is equivalent to 0.6 repeating. So it's repeating, so it falls under rational. Another one might be tricky to see, would be something like 2/11. Let's try that one. Or let's try 3/11. Anything over 11 would really work. 3 divided by 11. So again, my last number seems a little bit different, but otherwise there's this very distinct pattern. Okay, this is equivalent to 0.27 repeating. Okay, that 3 is because it was 2/7, and the 7 caused that 2 to get rounded up. But I can see the pattern and then just recognize that my calculator added that last piece of rounding in order to give it an end. And so it's a clear pattern, it repeats. That would still fall under rational, okay? A number like 17.38, rational. There is a distinct end, okay? A million, 2 billion, 375. Those are all numbers that end, okay? So they would be rational. Irrational is going to be a lot of those square roots where they don't fall on with a side length that is a whole number. Okay, we're thinking square root of 6, square root of 7, square root of 8. Square root of 9 would fall under rational because it's equivalent to the number 3, which is a number that has an end. Okay, but all those numbers in between are irrational. Square root of 4, I did not include for irrational because that equals 2. So that's a rational number. Okay, so that's just a brief overview of rational versus irrational. As I said, you have a Khan Academy quiz due this afternoon around 4 o'clock. So please take care of that. And I look forward to seeing you all again next week. I hope you have a wonderful weekend. And I don't know, reach out. There's some people I still haven't seen or heard yet, and I really miss you all. So please reach out as soon as you have time. Just send an email, reach out to me in Google Classroom, come to office hours, okay? I love seeing you all and hearing how you're doing and answering all of your questions. All right, happy Friday.